Hello and welcome to another lecture for Introduction to Astronomy. This is lecture number 8 in our series, and today we are going to be covering the giant planets in our solar system. Our learning objectives for this lecture today are we will go over the visual characteristics of the giant planets in our solar system, that is Jupiter, Saturn, Uranus, and Neptune. We'll go over their compositions and how there is metallic hydrogen in the core of Jupiter, which is pretty unique and pretty cool. There's also been several missions that have explored the outer parts of our solar system and the giant planets out there, such as Pioneer and the several Voyager missions. There's also been probe missions, which have been spacecraft that have actually sent little probes into the atmospheres of these giant planets, so we know very well what conditions are like in the atmospheres of these planets. And there's also some really cool storms and giant spots in the atmospheres of these planets. We all know that there is the Great Red Spot on Jupiter, but there's also the Great Dark Spot on Neptune. We're going to dust off our tool belt of astronomy techniques, and we're going to use comparative planetology again to talk about the giant planets in our solar system, or as they're sometimes known, the Jovian planets. And so these gas giants are very unlike the rocky terrestrial planets because they are not rocky and terrestrial, but instead composed and made up primarily of gases. They are gas giants. They are giant planets with very thick atmospheres of gas that surround pretty much metallic cores of hydrogen. So instead of having a solid surface, it is just gas all the way down until you hit the very densest part of the interior. So when we compare their appearances, we can see that there are several similar characteristics in that Jupiter and Saturn are similarly colored, whereas Neptune and Uranus are both blues. So they are all composed primarily of hydrogen and helium with some reduced compounds in their atmospheres. Jupiter and Saturn have a lot of ammonia crystals in their atmospheres, which give them those lovely beige colors, while Neptune has a lot of methane in its upper clouds. And there's actually very little cloud structure on Uranus, but Uranus is also blue tinted because of methane that is present. But it doesn't have as much cloud structure, it's just kind of diffuse gas. Jupiter is the most dynamic of the gas giants in that its uh, appearance has a lot of bands and stuff. There's a lot going on its surface compared to Uranus, for instance, which is just uniform in appearance. So Jupiter has a lot of these spiraling cloud structures, which we use to calculate the motion of the planet's atmosphere. However, the motion of the atmosphere is not actually the motion of the underlying planet. So despite Jupiter having one of the shortest days with a period of rotation of only 9 hours and 56 minutes. So it's it's a little tricky to calculate the exact rotational speed because the atmosphere is rotating at different rates than the entire planet itself. But Jupiter, being a gas giant, has a very short day since it's a lot easier for gas to rotate around quickly than it is for a rocky body like the terrestrial planets. So these are some images taken by Dr. Joseph McNeil. He's one of the other professors who teaches this course here at TSC. So here are some images that he and his wife and some friends took in town of Jupiter and Saturn. So we can actually see these planets fairly easily with our naked eye because they're very bright. And we can also really resolve their structures when we look through with telescopes or even simple binoculars. So it's a little tricky taking pictures through telescopes because cameras are a lot more sensitive than our eyes. So I will say that when we look through telescopes and binoculars at Saturn, it's a lot easier to see the ring structure and you can make out even some cloud bands on the surface a little bit. And whereas these photos are a little overexposed. But you don't need a telescope to see all these features. You can actually use relatively simple binoculars and be able to tell that Saturn has this elongated shape from the rings. And if the atmosphere is clear enough and your binoculars are more are powerful enough, you can actually resolve the gap between the planet and the rings. It's really cool, and I highly recommend doing that. If we were an in-person course, I would absolutely make us go do some astronomy together because that is one of my favorite things to do, which is guide students through observations. So if you are interested in doing your own observations and you want some tips, reach out to me because I would love to help guide you through looking at the night sky. So the gas giants, much like Earth and the other terrestrial planets, experience seasonal changes. Except really for Jupiter, since its axial tilt is only 3 degrees, as it orbits around the Sun and it rotates about its own axis, really not much changes because its tilt means that it's roughly always in the same inclination towards the Sun. However, Saturn and Neptune have some seasonal changes because their inclination angles are about 27 and 29 degrees respectively. However, Uranus has the weirdest seasons of all because it is tilted on its axis by 98 degrees. So that means that when we look at the image on the left of the planets and their relative tilts, we see that Uranus is tilted very, very weirdly compared to all the others. It is on its side. So as Uranus orbits around the sun, when we look at the image on the right, we see that its poles actually experience very long periods of darkness. So these are like 21-year periods of darkness at the poles as it orbits around the sun. So this gives us, if we think about a solar day as being how long it takes for a day and night cycle, since Uranus is tilted on its axis so much, its day and night is actually determined by its orbital position around the sun and not by its rotation about its own axis. So a solar day on Uranus is equivalent to its year. So the season changes on Uranus actually change from day to night as it experiences its year. It's very interesting and very weird. So the giant planets are very different in composition from the terrestrial planets, and they're also very far away. Jupiter is 5 AU out, meaning that is 5 times the distance between the Earth and the Sun on average. So Jupiter is very far out at 5 AU with an orbital period around the Sun of 12 years. Next up in the solar system is Saturn, which is at 10 AU and has nearly a 30-year orbital period around the Sun. As we go further out, Uranus is 19 AU and Neptune is 30 AU, with orbital periods of 84 and 165 years, respectively. So that makes understanding how they change during their years very difficult because it takes a very long time for them to have an entire year. So Jupiter and Saturn are very massive, with Jupiter being 3 times as massive as Saturn. So here we have their masses listed in terms of Earth masses. So that's what this M sub E stands for. So Jupiter weighs 318 times the mass of the Earth, while Saturn is 95 times the mass of the Earth. Uranus and Neptune are pretty small in comparison to Jupiter and Saturn, being 14 and 17 times the mass of the Earth, respectively. So this suggests that their compositions are very different, and indeed they are. Jupiter has an average density of 1.3 grams per cubic centimeter, while Saturn is much less dense at 0.7 grams per cubic centimeter, which means it is less dense than water. And the smaller of the giants, which we call the ice giants, have densities of 1.3 grams per cubic centimeter and 1.6 grams per cubic centimeter, despite being so small. And they have higher densities because they are composed of so much ice compared to Jupiter and Saturn, respectively. But this is like slushy ice in the atmosphere, not like a solid ice surface. Now let's talk about the compositions of these giant planets. So we can think of them as being very different from the terrestrial planets, and we refer to the compounds in these gas giants as either gases, ices, or rocks, based on the composition and not their state. So gases here, in this is in order of abundance in the giant planets. Gases are the most abundant element, with hydrogen and helium being in various states, and hydrogen and helium make up 99% of the mass of the outer solar system. So pretty much all of the mass in these giant planets is some form of hydrogen or helium. The ices refer to certain compounds that are the second most abundant, and these include compounds of oxygen, carbon, and nitrogen, which are found in forms of like water, methane, and ammonia, but also carbon monoxide and carbon dioxide, and these are all frozen compounds. And then there's also rocks, which are the rarest of the elements and the least and much less abundant than the ices, making up about less than 0.3% of the total mass of the outer solar system, and these are compressed states of magnesium, iron, and silicon, which have condensed down into the cores of these gas giant planets. So let's go over the differences in these giant planets and talk about how there's gas giants and the ice giants, which I kind of referred to earlier, but now let's go into more depth. So Saturn and Jupiter are called gas giants because they are composed almost entirely of the gas elements hydrogen and helium. But don't be fooled, while their heavy, dense atmospheres are in a gaseous state, their surface and interior are not gaseous but are compressed states of these gas elements. So this is where we get our metallic hydrogen. It's still a gaseous element in that it's hydrogen, but because it is compressed and under such high densities, it is now actually having the properties of a metal. So that's what we call metallic hydrogen. Uranus and Neptune are what we call gas giants because their compositions contain far more ices than gases compared to Jupiter and Saturn. But don't be fooled. There are still plenty of gases in their atmosphere. It's only just less relative to the ices. So the abundance of hydrogen and helium in the outer solar system is in a state referred to as reduced, meaning that all of these elements tend to combine or form some state with hydrogen forming first, and that dominates the compounds which make up these planets. There's some form of hydrogen compound. So like methane, which is CH4, or ammonia, NH3, ethane, C2H6, or acetylene, C2H2. So these, when we refer to them being reduced, this means that these gaseous elements, the hydrogen, well, helium's not going to bond with anything, but the gaseous elements, hydrogen, when we say it's reduced, that means it's forming compounds, these molecular compounds like methane and ammonia and whatnot. So I mentioned earlier that the interiors of these gas giants, particularly for Jupiter, start getting these weird states of hydrogen called metallic hydrogen. So let's kind of talk about that a little bit. We hypothesize that they are in the cores of these planets, and we can tell with pretty decent certainty from observational uh, observations, I guess, that they are likely present. So the densest states of hydrogen cannot be observed on Earth because they require immense, incredible, crazy amounts of pressure, nearly 100 million times that of the Earth's atmosphere. But we hypothesize that at these pressures, hydrogen behaves more like a solid and a metal because the electrons in their orbital shells are compressed so tightly that they pretty much become shared between the nuclei. And this means that the electrons flow, and we can think of this flow of charge as a current. And so this means that the hydrogen is conductive to charge, which is very much like a metal. So we call it metallic hydrogen. When there is less pressure, though, the state of hydrogen is a little bit more liquid. So we have what we call the liquid hydrogen, and that is more present in the lighter giants, and it doesn't reach the states to become metallic. And so we consider this liquid hydrogen to be primarily composed of what we call the molecular state, molecular hydrogen, because hydrogen can bond to itself a little bit. And so, with such immense pressures at the cores of these giants, they also retain some of their primordial heat as an internal energy source. And this is in all of the giants except Uranus, which no longer emits primordial heat. So, despite being so far away and uh, outside the range of where we could send humans currently, we have still managed to explore the outer parts of the solar system and the gas giants with spacecraft when the first mission, Pioneer 10, launched in 1972. There have only been 9 spacecraft total that have traveled beyond the asteroid belt, though. So, still very rare company to have traveled out that far. So, among these missions, with the latest being New Horizons and Juno still operating today, they have faced many challenges. So, obviously, being far away, the flight time to these gas giants is very long, sometimes decades to reach them. And being that far away, it can then take a very long time for the light and the electromagnetic signals from the spacecraft to reach back to Earth. So, it can take up to like almost a day for the communication to go from the satellite back to Earth and then for us to send a response back to the satellite out there. It can take a very long time because it's so far away. So the first spacecraft that we sent out to the outer solar system had pretty simple intentions. Their main objective was simply to determine if a spacecraft could navigate through the asteroid belt unscathed. So they were our Pioneer missions, Pioneer 10 and 11. And assuming uh, that they were able to make it through the asteroid belt unscathed, they also were intended to measure the radiation hazards of Jupiter. So Jupiter has a very strong magnetosphere, and so both Pioneer spacecraft experienced a lot of severe electronic damage as they went through the magnetosphere of Jupiter. And so this caused Pioneer 10 to drift off to the unknown edges of the solar system, while Pioneer 11 was a little bit more of an ambitious mission. It used Jupiter's gravitational field to slingshot the craft towards Saturn and confirmed that it was possible to do multi-planet exploration missions with a single craft, provided that you could have the planets in the right orbital positions at the right times, that your spacecraft on its journey could experience the gravitational tugs of each one at the right time. So understanding where the planets are in their orbits is very important for planning out space missions. Not only because you want to be there, not only because you want your destination to be there when your craft arrives, but because you need to navigate there correctly. Voyager 1 and 2 are really the stars of the spacecraft that have explored the outer parts of the solar system, and they are actually now beginning to reach the edges of what we call the solar system. So in 1977, Voyager 1 and 2 were launched, and in 1979, Voyager 1 was the first spacecraft that was sent to study Jupiter and Saturn, and it was capable of taking photos. However, it was the immediate sister craft, Voyager 2, that really managed to do some spectacular things. So in July 1979, Voyager 2 had 11 scientific instruments attached to it, and it arrived at Jupiter. And this was because during 1979 to 1989, the outer solar system was what we call in planetary alignment, which occurs once every 175 years. This meant that Voyager 2 could not only visit Jupiter in 1979, but then it visited Saturn right after in 1981, and then was actually able to visit Uranus in 86 and Neptune in 89. This is referred to as astronomers as the Grand Tour, and it was a Massive scientific achievement, and it gave us our first glimpses at the outer solar system up close as a whole. And so, uh, these days, the Voyager 1 and 2 spacecraft are still traveling out in space, and they are currently the most distant spacecraft ever launched by humanity. The Pioneer's locations are unknown because of the damage they uh, incurred due to Jupiter's magnetosphere. So no one actually knows where the Pioneer spacecraft are. They are very small, they're not emitting anything, and so maybe someday someone will be able to go find them. So not only have we sent spacecraft on long missions through the solar system, but we have also sent some to the outer planets to orbit them. So these are the giant planet orbiters. Galileo, Cassini, and Juno were all missions that were orbiter missions intended to provide long-term detailed studies of the gas giants. Galileo was the first spacecraft to enter a probe into Jupiter's outer atmosphere. The Galileo probe had a descent where it reached speeds of 50 kilometers per second, the highest speed of any probe, where it experienced atmosphere friction of 27,000 degrees Fahrenheit before its parachute deployed for nearly an hour, and eventually the probe dematerialized. It kind of came apart. But after probing the atmosphere, the Galileo main rocket jettisoned itself into orbit to study the Galilean moons. These are Io, Europa, Ganymede, and Callisto. These are the four moons that Galileo saw with his telescope that we talked about earlier in the semester. There was also the Cassini mission, which was a multi-fold Saturn mission, which studied the rings, moons, and planet itself, Saturn. And also, most recently, we had the Juno mission, which had a simple color camera attached to it called the Juno Cam, which gave us a lot of pretty pictures. But that was not the main scientific goal of the Juno mission. However, it was a great way for the public to interact with astronomy because JunoCam images were made available to the public to process and give us our own experience with astronomical data. The magnetic fields of these gas giants have long been enticing to astronomers and physicists because in the 1950s unusual radio waves were detected emitting from Jupiter. But these were not aliens, but instead due to the magnetic field of Jupiter interacting with the charged particles from the Sun. As charged particles traveled quickly through the strong magnetic fields, they give off some electromagnetic waves, which we call synchrotron emission. So these are perfectly natural radio emissions from Jupiter, which were puzzling at first, but made sense once physicists were able to come up with some physics theories. And it was later determined that the radiation was not coming from Jupiter itself, but the area surrounding Jupiter. This was the magnetic field trapping those charged particles. Jupiter's magnetic field is not, its magnetosphere is not just due to the planet itself, but also by volcanic activity on some of its nearby moons, including Io. Each gas giant has a magnetic field, but Jupiter is by far the strongest. But there is actually a slight mystery today still with the magnetosphere, and that is because these magnetic fields are not aligned directly with the axis of rotation of the planet. So thanks to our probes from these spacecraft when they visited these gas giants, we know a lot about their atmospheres. However, when we first started taking spectra of astronomical objects as early as the 1930s, we could determine a little bit about their composition. However, we didn't know exactly what it was because when spectroscopy was still a young field, we weren't able to resolve things as clearly and we couldn't make out what all of the spectral features were. So they could tell that there was methane and ammonia, but it wasn't until we sent probes that we could tell that hydrogen and helium were the dominant elements. And this is because when we look at their spectra, they have simple spectral lines, and so it wasn't quite clear that these were the most abundant elements. And it wasn't until the Voyager missions gave us some far infrared spectra that we were able to see that hydrogen and helium were indeed the most dominant elements in their atmospheres. And it was then deduced that Saturn and Jupiter have similar atmospheres, with Saturn being slightly less helium abundant. Jupiter has more helium than Saturn does. From studying these atmospheres and their changes with our spacecraft, we know a little bit about the weather and the wind patterns on these planets. So these gas giants have very dynamic atmospheres with intense convections, and they rotate very fast about their axes. And so this causes the motions of their upper clouds to create circular patterns which are horizontal, which are very visually alluring. So Jupiter has the most appealing atmosphere in terms of visuals because it's got a lot going on. It's a very complex atmosphere and it has the most rapid period of rotation. And so these patterns can be used to determine the conditions and the wind speeds throughout the atmosphere, and we can even learn down to a little bit down to where it becomes a liquid surface. So we can learn a lot about the gaseous part of these atmospheres by studying their wind patterns and their weather patterns. So on the image we can see plotted on the latitude of the planet, we can see the eastward wind speed. So we can see on Jupiter that its winds are strongest near the equator, and up near the poles, it's a little bit back and forth. But overall, Jupiter has wind speeds that are primarily going towards the east. Saturn also has primarily eastward winds. But then we look at Uranus, which is tilted on its side, and it's got a very interesting wind distribution pattern because it has less drastic convection cycles. But Neptune actually has the most intense winds of all, with winds reaching supersonic speeds, nearly 2,100 kilometers per hour in the eastward direction, which actually exceeds the speed of sound in Neptune's atmosphere. So that is very, very windy. You would want to pack a hat for sure. And if we've got crazy high winds, well, we've probably got some crazy giant storms on these giant planets. So along with all of these convection currents in their atmosphere, we can also find a lot of nearly permanent storms. The largest and most famous and most prominent of these storms are the Great Red Spot on Jupiter and the Great Dark Spot on Neptune. So Jupiter's Great Red Spot is a long-lasting storm that is a red oval in the southern hemisphere, which is known to change very slowly and includes many small white ovals, which are smaller storms, which surround it. It has persisted for a very long time, so long that astronomers saw it when they first looked at Jupiter 300 years ago with their first telescopes, and it continues to this day, although it is actually shrinking. So it is assumed that the storm could actually end in the coming decades. I say coming decades, that could still be about 20 decades. Like that could be 200 years from now, the storm may finally shrink and disappear. So it's very fortunate for us that we're able to see it and know that it has such a cool storm, the Great Red Spot. And it's also unique in that it is rotating counterclockwise in the region. Is rotating counterclockwise in regions of high pressure, which is different than storms on Earth. Neptune's Great Dark Spot is also a bit of an anomaly. It was first detected by the Voyager spacecraft and it is very similar to the Great Red Spot because it is also located in the southern hemisphere. But by the time the Hubble Space Telescope observed Neptune in the 90s, the Great Dark Spot had disappeared, making it a little bit of a mystery. So this also points to Jupiter's Great Red Spot potentially being a very temporary feature. So get out there and observe it while you can. This brings us to the end of our lectures on the gas giants.